So here we are. I've redrawn the diagram here. I hope it makes sense. We have this mass, it's on a 20-degree incline. They gave you the two coefficients of friction and the value for M2. And in part A, you're supposed to find this mass, and in part B, you're supposed to find the acceleration if you give it a nudge to overcome static friction. So the first thing we're going to do, of course, is to do the free body diagrams. So here's for M, the mass that's sitting there on the hill. So it has mg pointing down. It has normal force going this way, and then tension going up the hill and friction going down the hill, like that. For the hanging mass, we have the tension going up and m2g going down. When I want to write my equations, I'm going to need axes. So I'm going to put the y-axis down through the normal force, because that's a good idea, and the x-axis this way. Now see, I have 1, 2, 3 vectors flat on the axes, but it's this mg vector that's slantways. So I'm going to need the angle between the x-axis and the mg vector, this angle, which I realize is that angle up there. That's not 20, that's 70. So I'm going to put a 70 in here. All right, so for part A, we're going to write our equations, and I'm going to start with M, the one that's sitting on the hill. So the x equation for M is going to have tension and friction in it. Tension to the right, so it's positive. Friction to the left, so it's negative. And now the mg is also to the left, so I'm going to do minus mg. And this is the x equation, so I do cosine, and I do the angle, which is 70. All right. Now, for this part, this is going to be equal to 0 because it's not moving. The y equation is going to have the normal force pointing up, and then the y component of mg, which is minus, because it's going down, mg sine 70, because this is the y equation, and that's also going to be equal to 0. We have friction equals mu times the normal force. And in this case, it's mu sub s, because it's not yet moving. And we can say that it's equal because it's only just barely not moving. For the hanging mass, we have this right here. There's only one equation. Tension is up, m2g is down, and this is also going to be equal to 0 because it's not moving either. So to find the m that's not m2, to find this m here, I need to kind of put all of those equations together. So I'm going to put, from this equation, I'm going to put t equals mg, m2g like this. I'm going to put that in there. From the friction equation, I'm going to use friction equals mu sub s times the normal force. But from this equation, I can see that the normal force is equal to mg sine 70. So that's going to be mu mg sine 70. And I put that all together, and I get m2g minus mu mg sine 70 minus mg cosine 70 equals 0. And from here, I should be able to find m. Now, in part B, I'm going to do the same free body diagrams as before, but now it's going to be sliding friction, and now they're going to accelerate. So that's going to change this equation slightly. It's going to be t minus f minus mg cosine 70 equals ma. And this one stays exactly the same, n minus mg sine 70 equals 0. And this one becomes friction equals mu sub k times the normal force. This one is going to, as this guy goes up, as this one here goes up, this guy's going to go down. So that's t minus m2g is equal to minus m2a. So now we have 4 more equations that we can put together. This time we're looking for A. So from this equation right here, I'm going to figure out that tension is equal to m2g minus m2a, and that's going to go in there. Friction, just like before, friction is equal to mu times the normal force, which, just like this, it's mu mg sine 70, but the difference is that this is now mu sub k. And so I put that all together, and I get something that's probably too big to fit on this line. Let's make myself some room here. So I'm going to say tension, which is m2g minus m2a, minus friction, which is mu sub k mg sine 70, minus mg cosine 70 is equal to ma. And after that is just algebra. Get this term with a over to that side, factor out a, divide, plug the numbers in. You're good to go.